Hello everyone, welcome to the 36th lecture in the series. In this lecture, we are going to learn about Strassens multiplication. So, it is a multiplication that is applied for matrices, and we are going to see how divide and conquer approach is applied for matrix multiplication and how this Strassens multiplication is better than the conventional matrix multiplication we do, and how it helps in improving the time complexity. So, let us first see how this standard matrix multiplication happens and what is its time complexity and what revisions we actually make in this Strassens approach using the divide and conquer approach that we have learnt already, and then we will see the improvement of this Strassens multiplication over the conventional matrix multiplication. So, let us first see how this basic matrix multiplication we are doing. So, consider that we have two n by n matrices A and B. So, we are going to define matrix multiplication as A cross B. The resultant is going to be C, which is also going to be an n by n matrix, and for every index I comma j in the resultant matrix C, we are going to do this computation. We are considering row I of the first matrix A and column j of the second matrix B, and we are going to multiply their entries together, first entry of the row and the column, the second entry with second, likewise we are going to repeat, and finally we are going to add up all the products, and that will give you the result for doing a multiplication. And not only that, we may have to do some scalar operations like addition or subtraction, and overall when we consider the time complexity of the basic or conventional matrix multiplication, it is going to be order of n cube. So, now we are going to learn, after learning this divide and conquer approach, we are going to see how it could be applied to further bring down this time complexity from order of n cube to something less than this. So, here you could see here we have the two matrices. I hope you remember that those two matrices are of size n by n, and so we have taken only a square matrix, that is to be noted, and we are going to multiply A and B to probably get the resultant C. So, for getting this resultant C, as such since A and B are of size 2 by 2, this resultant will also be of size 2 by 2, and the C11 has been obtained by multiplying the first row with the first column. So, the first C11 has been obtained by A11 into B11 plus A12 into B21, and that is how we have got the first element of the resultant matrix C. Likewise, we have been doing for the other elements of this resultant matrix, and this is the conventional way of doing. So, altogether what you need to know is that just for the sake of multiplying this 2 by 2 matrices, we may have to do 8 matrix multiplications, as you see here for C11 to C22, and we are doing 4 number of additions. So, here when you look at the time complexity, so the 2 by 2 matrix multiplication can be accomplished with 8 multiplications, and of course, that is going to be 2 log 8 base 2, and which is roughly 2 cube, and so we say that the complexity is of the order of n cube. So, this is the routine way of doing this basic matrix multiplication. We are taking elements from those two matrices, and we are computing C of I j, but actually what we do is that every time when we write the code, we multiply elements at location A of I k with k j, and you could see here the use of 3 indices, and so naturally for implementation we may have to use 3 nested for loops, and so we say that this basic matrix multiplication is going to have a complexity of the order of n cube. So, I believe that by this time you might have even learnt this matrix multiplication with your C programming course, and that is the reason why I have not put up the actual code for doing a matrix multiplication. You know, just by seeing this, you know that we multiply Aik with Bkj, and so we are supposed to maintain 3 indices, and that is the reason we have 3 nested for loops, and the order is of the time complexity is of the order of n cube. So, what Strassen has done is that he has shown that we can do that same 2 by 2 matrix multiplication with just 7 multiplications instead of 8, and instead of having 4 additions we could do that with 18 number of additions and subtractions. So, you may wonder that we have just reduced multiplication by 1, on the other hand the number of additions or subtractions have been 4 times more, and how this Strassen could be better. But the principle is that always addition and subtraction operations are considered to be of best than that of multiplication and division. Addition and subtraction are considered to be cheaper than doing multiplication and division. So, how we have to perceive this is that we have replaced one multiplication with, say for instance 14 number of additions and subtractions, even then it is going to be considered cheaper than before. So, we are going to achieve this Strassen's approach by probably following the divide and conquer approach. You know what divide and conquer is by this time. We will be dividing the original array into several subpartitions, then we will be conquering it and conquering each of those subpartitions separately, and finally merging the results. So, the same thing we are going to apply here with Strassen's matrix multiplication. So, this is the general way of doing this divide and conquer. So, it is a general algorithmic design paradigm or algorithmic design strategy, where we have the original data S, which is divided into 2 or more disjoint subsets, say S1 and S2, and then we will be recursively solving each of the sub problems, and finally we will be combining the solutions of those disjoint subsets S1 and S2 in order to get the original solution for S. As such, since whenever we use a recursive approach, we are supposed to use recurrence relations or equations, and every recurrence relation will have a base case and a recursive step. So, here let us consider how we could use divide and conquer on matrix multiplication. So, given an array A and an array B, both of them are 2 dimensional arrays. So, we say them as a matrix. So, both of them are square matrices, and we have partitioned A into 4 subpartitions and B into 4 subpartitions, and for each of the partitions we are applying actually repeated multiplication and addition in order to get the final results. So, we divide the matrices into submatrices A0, A1, A2, etc., and then we use blocked matrix multiply equations, that is, this is what we mean as equations, and finally we recursively multiply each of those submatrices to get the result for this matrix multiplication. So, now let us investigate this recursive version of the matrix multiplication, where we divide the original matrix into 4 submatrices. Each of those submatrices will be used for computing resultant matrix, which is C in our case. And as we know, this 2 by 2 matrix may involve 8 matrix multiplications involving 4 submatrices of A and 4 submatrices of B. Not only that, we may have to do some sort of addition and subtraction here, and that is what we mean as some scalar operations, and we believe that those scalar operations take up a time of order of n square. So, as such, since we are using this divide and conquer approach for matrix multiplication, we may have to have a base case, and the base case is that when the array contains either 0 or 1 element, in that case we straight away multiply them, and that is going to be our resultant, and this is going to be the terminating case for our recursive problem. And for all other cases, then we may have to recursively apply multiplication and those scalar operations to get the results. Strassen in 1969 observed that the product of 2 matrices can be computed using this divide and conquer approach as given below. Like what he has done is that he has divided the original matrix into 4 subpartitions like as you see here, we have shown them as 4 subpartitions of A and 4 subpartitions of B, and we are going to multiply elements from each of those subpartitions in order to get the resultant matrix. So, he has used some formulae to compute to make this happen. So, you could see that the first C naught naught has been obtained by doing M1 plus M4 minus M5 plus M7. The C naught 1 has been obtained by summing up M3 and M5. C10 is obtained by summing up M2 and M4, and C11 has been obtained by summing up M1 and M3, and the result should be subtracted from the result of M2 plus M6. So, now let us see how this M1, M2 up to M6 has to be computed in this case. So, here we could see the detailed way of how this Strassens matrix multiplication is actually working. We are doing 7 multiplications starting from P1 to P7. So, product 1 is A11 plus A22 multiplied by B11 plus B22. So, A11 and A22 are here, they are summed up first and then they are multiplied with the sum of B11 and B22. Likewise, we are doing 7 number of multiplications. Here you could see the star symbol everywhere. And finally, what we do is that we are doing some scalar operations. So, this plus and minus is what we mean as scalar operations, and we are doing some 4 steps of scalar iterations, scalar operations for each of the 4 elements in the resultant matrix. That is what we have put up here. So, as such the first element, that is C11, is obtained by adding P1 with P4, and the resultant is subtracted from P5, and to the result we add up P7. So, what we have done is that we have substituted the value for P1, P4, P5 and P7, which we saw with this previous slide. So, those values are substituted here for the computation of C11. So, for any square matrix, we are supposed to find this 7 number of multiplications followed by 4 number of scalar operations. So, here as I said before, Strassens, this approach relies on divide and conquer. So, here since we have taken a 2 by 2, we have just divided into 4 subsets. If the matrix had been somehow bigger, then we may have to repeatedly divide it into square matrices of size 2 by 2 and perform this computation and recursively do the same for every 2 by 2 matrices. So, yet another thing you should note is that in order to do this Strassens matrix multiplication, your original matrix should be square. If not, we may have to do some extra padding in order to make the original matrix square before we do this Strassens approach for matrix multiplication. So, in short, this Strassens algorithm can be put up this way. We are doing a matrix multiplication of 2 matrices, namely A and B, and we are having pointers to them, and we are having the resultant as R, and that is going to be the pointer for the resultant matrix R, and n represents the number of elements. When n is 1, that is our base case, we are just going to multiply straightforwardly the element in A and B, and that is going to be the resultant. Otherwise, we may have to do these 7 steps of multiplication and 4 steps of scalar operations to get the result for this matrix multiplication using this Strassens approach. So, here the thing to be noted is that the Strassens approach has drastically reduced the number of multiplications to be performed on the matrices from 8 to 7. So, accordingly, we may have to revise the recurrence relation for the new algorithm, that is the Strassens algorithm. So, as such, since we are dividing the data set by 2 every time, it is going to be T of n by 2. 7 times we are going to apply product. So, it is 7 into T of n by 2 plus the scalar operation, as we know, it takes up a time of order of n square. So, this is going to be the recursive step for this recurrence relation. So, for instance, if you take the time analysis of this Strassens multiplication, you know, when we have only one element in each of those input arrays A and B, then our T of 1 should be 1. when we have n number of elements and we assume that n is equivalent to 2 power k, then our T of n should be 7 times T of n by 2, where n by 2 corresponds to each of those partitions we have, and so this time should be 7 times 7 power k, and when we sum up, our total time should be 7 power log n, and this could be rewritten as n into log 7. So, our complexity would be of the order of roughly n power 2.81. So, you know, Strassens approach takes up a time of order of n power 2.81, whereas the conventional matrix multiplication takes up order of n power 3. So, to you it may look simple that 2.81 is almost 3, but you should note that this is actually an exponent. So, 2.81 is an exponent, and so when n is considerably large, n power 2.81 is going to be very less than n power 3. So, that is why we say that Strassens approach is better than the conventional approach for doing matrix multiplication. So, in short, when we compare the time complexity of the conventional way of matrix multiplication, it takes up 8 multiplications plus some scalar operations, which is going to be of the order of n cube, whereas Strassens approach has reduced the complexity from 8 multiplications to 7 multiplications plus some scalar operations, and so it is going to be of the order of n power 2.81, and as such this 2.81 is an exponent, and so we say that it is very cheaper than the order of n cube as we have with conventional matrix multiplication. So, these are some of the things that we need to know, that Strassens algorithm is not always practical. The constant factor is somehow larger than that we use for naive method, that is the scalar operations is more than that we do for conventional matrix multiplication, and so that is what we mean here, and specially designed methods are somehow better than this for sparse matrices. And this recursion also uses, whenever there is recursion, you know that it takes up lots of space in memory. So, these are all some of the drawbacks of this Strassens algorithm, and we do not say that this algorithm is the fastest known method. There are certain other algorithms which even claim to have an order of up to n power 2.3, whereas Strassens approach has n power 2.8. So, we do not claim that Strassens algorithm is the best for doing matrix multiplication. So, here I have put up some of the limitations of Strassens algorithm. One is that it has numerical instability. So, when the number of additions as well as subtractions is more, as we witnessed, it has around some 18 additions and subtractions. There could be some rounding of errors since we deal with floating point arithmetic. Yet another limitation could be the overhead we face. When the input matrix is really small, then it is not worth to go for this recursive approach, because always, you know, recursive approach is a bit slower and more space occupying than the conventional way of doing, and so we say that to be a overhead. And you know, one of the constraints that we have with the Strassens multiplication is that the input matrix should be square, and if not square, we may have to do some sort of padding, and so that is claimed to be one of the disadvantages. And as such, the implementation is a bit complicated than just because it uses some formulae to implement, and when it comes to debugging also, it poses slightly challenge because we are not well versed with those equations. So, these are all some of the limitations of Strassens algorithm. So, to summarize what we have seen, this Strassens algorithm relies on divide and conquer approach. It splits the original matrix into 4 submatrices, and at the conquer step we are applying some recursive 7 number of multiplications on those submatrices, and finally we are merging up the results and to get the final result of matrix multiplication. So, let us now look at some of the review questions to test our understanding on Strassens approach for matrix multiplication. So, how does this Strassens algorithm reduce the number of multiplications and why it is important? So, when the matrix size is huge, Strassens algorithm reduces the number of multiplications from 8 to 7, and because of this particular step, what happens is that the overall time complexity drops down from order of n cube to order of n power 2.8, and that is said to be one of the significant improvement in time complexity when we do Strassens approach for matrix multiplication. Explain how the divide, conquer and combine steps are used in Strassens matrix multiplication. As you know, in the divide step, what we do is that we are dividing the original large matrix into 4 submatrices, and in the conquer step we are applying roughly 7 recursive multiplications followed by some 14 scalar operations, and to get the result for that particular submatrix. Finally, we will be merging the results of all the submatrices to get the result for the original large matrix. And why does Strassens algorithm have a lower time complexity than classical multiplication, and what is the time complexity? So, we know Strassens algorithm takes up a time of order of n power 2.81, and you know the reason behind is that the number of multiplication is reduced, and we can't think of it as just reduction in multiplication by a factor of 1. So, here always multiplication is considered to be an expensive operation than addition and subtraction, and so we say that reduction in time complexity from order of n cube to order of n power 2.81 is going to be significant improvement in time complexity. And what are all the limitations of Strassens algorithm in practical applications, or for especially for smaller matrices or floating point? So, when the matrix size is small, it is not good that we stick on to some recursive approach for doing this matrix multiplication. It is better that stick on to conventional one, and as such since it employs lot of scalar operations, and that will not give you the exact result at times since we are dealing with floating point arithmetic. When the input matrix is not square, then we may have to spend some time on doing padding to make the original one a square matrix, and that takes up extra time. And slightly we view Strassens approach a bit complex one just because it relies on some standard equations, and when we have to look at debugging aspect, then that is going to be a bit challenging. So, these are some of the limitations of Strassens algorithm. Hope you are now thorough with using the divide and conquer approach using the Strassens algorithm for matrix multiplication, and thank